So yeah, I'm going to tell you about some work we've been doing on what's called quantum sensor magnetic resonance. And what I wanted to do in this talk was to give you an overview of the field and the frontier kind of questions that people want to ask with it, and also some sort of more recent results. So let me just set the stage here by saying that, as a group, we are very interested in nuclear spins. And, quite interesting, my own career trajectory has come from quantum computing and whatnot, but I got very interested in nuclear spins because A, they are in everything, and B, they're very coherent quantum objects. So, you take a crystal out of the ground and you look at it, and, you've got atoms, and, many of these atoms are endowed with spin. Um, so these nuclear spins are sort of the engines of NMR. And NMR has been going around for 50 years or so, but it's such a forgiving field because there are many ways in which you can enter NMR and magnetic resonance in general. But it all relies on the fact that these nuclear spins are very highly coherent objects that you can manipulate from the outside. So why NMR became very popular is because it was realized that not only can you probe these nuclear spins from the outside and look at them, but also these nuclear spins sort of report on their local chemical environment. So you can take a molecule like this is my favorite molecule, coffee, and you can look at different nuclei and you can kind of just see them, and you can see the local electronic structure around it. And so it became a sort of indispensable tool for chemists for sort of structure determination. Um, and if you've got now like sugar in your coffee, you can also see peaks of glucose, and so you can kind of tell your sugar is sweet, but with $1 million tool. So it's NMR has come a long way in the sort of analytical capabilities that it can enable. But really the power of NMR actually resides in the fact that you are probing quantum mechanical objects from the outside world. And these nuclei are quite remarkable. Even without doing anything for free, they have very long lifetimes, which means you prepare the nuclear spin in a particular state. And how long will it remain in this state? And this can remain there for tens of minutes for free without doing too much. And they also have very long coherence times, which means you prepare the spin in a superposition state. Yeah, you prepare it along the Bloch sphere, along the equator, and these spins in a magnetic field will precess. And these precession times can be, few seconds, while every precession period is like, tens of nanoseconds. So you can one zip in 10 nanoseconds, and you can precess for a few seconds. That's like 1 billion or so precessions of these nuclei without doing anything to the sample, and just taking sort of a garden variety sample. So nuclei are very nice, and in some sense that's because they're protected from the outside world. Nuclei have these very nice properties. Apart from this, apart from the fact that you can see them and they're very coherent, so you can kind of put them together and you can actually manipulate the interaction Hamiltonian between nuclei. And this, in my opinion, is one of the key strengths of NMR in general. And so here is a network of spins. And you can write down the Hamiltonian, which describes the interaction between the spins. And this is an all-to-all interaction. So every spin interacts with everything else, with a dipole-dipole interaction form. So it's every spin is like a small magnetic dipole and interacts with some of the dipole. But because they're so coherent and they're relatively weak in coupling, you can manipulate the interaction between the spins. So you can start with a natural Hamiltonian, which is the Hamiltonian of the spins just out of the ground, and you can apply control fields from the outside, and you can change them. So you can actually almost make the interactions disappear effectively, and that's called decoupling. So you can, on average, make the spins have no coupling, and you can also make it such that the couplings reverse in sign. And all of these things are, in some sense, quite mind-boggling, and all of this is possible because of the sort of remarkable properties of nuclei in general. And it's sort of agnostic of the system. Generally, nuclei are very easy to manipulate. They have long coherence times, and you can play all these tricks from the outside world. So, so NMR is very powerful because it is the technique that one uses to study nuclear spins and the interaction between nuclear spins, and the interaction between nuclear spins directly reports on structure, for instance. And so, indeed, the whole power of whole power of NMR resides in the power of inherent in nuclear spins. There's a problem, however, and the problem is that it's not easy to see these nuclear spins. So to see them, first you need to prepare them, and you need to sort of read them out. So while nuclear spins are in everything, in you and me and every other object you can see around us, it's not very easy to access the power that's buried inside them. You first have to prepare them, and to prepare them, you need a large magnet. So typically, you put spins in a magnet, and these spins are like little magnets themselves, and they align in the direction of the magnetic field. Equivalently, you open the energy gap between spin down and spin up that's proportional to the magnetic field, and you get a population imbalance between the two states. And this is what you measure with NMR. And this population imbalance can be extremely small, right? So even at a large magnetic field like 7 Tesla, carbon-13, which is a very popular nucleus, has only a population difference, or what's called polarization, of about 10 part per million. So it's a very weak signal. Also, the detection is done through RF coils, and that's because how detection works is you let spins process inside a coil, and they induce a current in a coil because of Faraday induction. And these coils are large macroscopic objects, so it's very difficult to, for instance, shrink down NMR to length scale of a single molecule or a single cell and so forth. So all detection is done in macroscopic length scales. Also, all spins of the same species, when you put them in a magnet, are polarized approximately equally. So it's very difficult to study non-equilibrium phenomena. Well, the interaction Hamiltonian, which is the interaction, these sort of bonds that are shown here, which is every spin interacting with everything else, is actually very powerful and can be exploited much more if one can, for instance, selectively polarize only one spin out of the network. So, broadly, while NMR is very powerful, there have been triumphs of human triumphs in 2D NMR, MRI, and whatnot, which have all been rewarded with Nobel Prizes. The current paradigm of NMR is that nuclear spins are in everything. Nuclear spins are very powerful, but to see these nuclear spins, you've got to physically take the sample into an NMR machine. All right, so that's the sort of paradigm of NMR. And you have to take your sample, you have to crush it and make it a powder, or you have to dissolve it in a solvent and take this liquid, put it in a test tube, walk down to your NMR facility, and go down to this large magnet and put your sample into the magnet, and then you do NMR with it. So that's sort of the paradigm of NMR as it exists. So as a community, we are generally interested in this whole field of sort of quantum sensing and NMR. It tries to sort of invert this paradigm. So instead of taking the sample to an NMR machine, what we want to do is actually bring NMR to the sample, sort of convert completely 180 degrees, inverting this paradigm. And I'll show you how this is potentially possible. And this relies on some sort of special nanoparticles of wide bandgap semiconductor materials, and I'll show you how. But a classic example is diamond. This is a nanoparticle of diamond. And so it turns out that, quite interestingly, because of the properties of this material, it turns out you can take this material and make it appear as if it was a polarizer. So it plays the role of a large magnet as well as a detector or an RF coil in an NMR experiment, and you can address this with light. So this nanoparticle, which can go anywhere between 100 nanometers and to microns and much larger, can by shining light on it, and with the wonders of PowerPoint, you can kind of combine them together. But indeed, the goal of a lot of our research is to try to see how we can take these nanoparticles and make them play the role of an NMR spectrometer. And the role of an NMR spectrometer is to first polarize the spins, sort of align them in a magnetic field, and detect the spins. And both of these roles can be played by these nanoparticles. And that's sort of the focus of my group. And so let me just give you a flavor of how this works, and feel free to stop me anytime. So it turns out that these nanoparticles are made of, let's assume that they are made of diamond, and this is a classic material that makes it work. So these nanoparticles have nuclear spins within them, and it turns out that if you shine light on these nuclear spins, they can be very highly optically polarized to a level that's equivalent to putting them in a large magnet, sort of incredibly large magnet. So one way to think about it is, conventionally, when you put these spins in a magnet, they are only polarized to some, 10 part per million or so. But by shining light on them, these spins can be polarized to 1% or 10%, between 1 and 10%. It's in field units, this is equivalent to putting the spins in a very large magnetic field of the order of thousands of Tesla. And these nuclear spins exist everywhere, including on the surface. So you can shine light on them, and these nuclear spins can be polarized, and these nuclear spins can then act as an injection agent of polarization to the real world, outside world, and sort of playing the role of a large magnet. It also turns out that these nanoparticles host electrons in them, and these electronic spins can act as NMR detectors. They can sort of act as NMR detectors of their outside world. And more importantly, because they are housed in a nanoparticle volume, we can get all the advantages that people doing nanoscience get, high surface area of these particles, but more importantly, the ability to target these particles to a particular spatial location of interest. And this targeting can be done either physically, so you can move the particles, and I'll show you some results, where you can move the particles physically, either using a laser tweezer or a microfluidics or something. You can put them in a vehicle and move them, or you can target them chemically, so you can functionalize the surface of the particles. And we work with Olga, I think she's here on the call, but Olga Shenderova, who's in your neighborhood, but she's one of the experts in diamond functionalization, is able to sort of control both the hydrophilicity and phobicity of the surface of the diamond, also make functional groups that can sort of target these nanoparticles to any analyte of interest, a large variety of analytes of interest. So it could be single cells, there could be specific analytes of interest. So you can really rely on the. So one of the interesting features of the system is that you get all the sort of light-driven, nice features of nuclear and electronic spins, but it is in the solid-state platform that can be physically transported. So at the interface, though, so if you sit at this and you combine these features, it allows one to use the nuclear spins as the polarizer, use the electronic spins as a detector, and transport it. So you can have essentially you can be able to effectively bring an NMR spectrometer to the sample rather than bringing the sample to NMR. So let me just give you some flavor of the system in the context of diamond. But I want to emphasize that diamond is not the only system where this works, and it also works in silicon carbide and whatnot. In diamond, the nuclear spins are carbon-13, and you can make diamond with a lot of C13 or not. These are the spins that are very highly polarized with light. And the electrons are defects, which are called NV centers. And these are, and I'll tell you more about them, but they're defects in the lattice. And this is what these particles look like. They're very pretty. They're pink diamond nanoparticles, and they're relatively low cost to manufacture. So anyway, so in the focus of the talk today is actually, I'm going to emphasize some very special, nice features of these nuclear spins, which are carbon-13 in diamond, and show you how you can actually exploit them for some of these properties of deployable NMR. You want to bring NMR into the sample. So here's a cartoon of a diamond particle. It's got these defects, which are NV centers, and it's got C13 nuclear spins. It so turns out if you shine light on these nuclear spins, as I told you, you can hyperpolarize them, but that's like a single shot NMR signal from C13 in diamond, and about 1 milligram of diamond, and it's a very large SNR. And that's because these spins have been so highly polarized that it's very easy to detect them with NMR or MRI. These signals have been accelerated by a very large factor. It also turns out that not only can you see them easily, they also are very highly coherent. So these graphs that I showed on the first slide are actually on our C13 in diamond. So you can set them processing in a magnetic field, and they process for a few seconds, approaching 10 seconds. Each procession time is 10 nanoseconds or so, and you can easily complete 1 billion oscillations of these spins. So they're very highly coherent, and it's important to realize that these spins are full. These samples are full of electrons. They're full of junk, and they're kind of not very well prepared and whatnot, but they still are very highly coherent. And they're also very highly long-lived. So you can prepare the spin in a particular state, and you can go have coffee and come back, and the spins remain there so for tens of minutes. And all of this is in a solid-state platform. And they are really nanoparticles, and you can play all these nice games with nanoparticles. So what we've been trying to do is actually put nanoparticles in vehicles, and I'll show you some slides later. But and these are vehicles of microfluidic droplets. So this is a droplet of water and oil, and these red things that you see here are nanodiamonds, and they can be loaded in these droplets, inside the droplets, and you can physically move the particles in the droplet. You might ask why that's important, and I'll tell you more. But you can essentially make both transportable NMR detectors as well as transportable polarization agents and physically move it. And this is one vehicle by which you can move it. So anyway, what I wanted to give a flavor to, however, in this talk is to give you a flavor of what kind of things you can do. And I want to emphasize this is very much an active area of research. So several of these things are still out there. I think they're a few years away. But the system, I think the forgiveness of the system allows us as a community to envision sort of interesting applications that one could bring to bear on the system. So one of which is, a laser hyperpolarized NMR, means by which you can use the nanoparticles not as a transportable agent, but use it as a very material with a very high surface area. So you can take these particles, almost make a sponge of diamond or a large surface area of material, and you can use it to hyperpolarize other materials through the carbon-13 that's in the diamond, and sort of make hyperpolarization agents which are optically driven. It's also possible to use the same system to make very highly coherent quantum sensors, and I'll tell you more about it. But a quantum sensor essentially is a very sensitive magnetic field detector and can be used for NMR as an NMR sensor, but also as a magnetic field sensor. And it's possible now because you have these very highly coherent spins, but coherent spins that you can easily detect. And so you can make very highly coherent sensors. It's also possible because of the fact that you can detect NMR signals with light to be able to localize NMR signatures to very nanoscale volumes. So this could be NMR of a surface or an interface, or you can use these particles in a droplet or some sort of transportable vehicle as an NMR sensor. So you can make a sensor that's transportable physically. And there are also a lot of applications in quantum information science because hyperpolarization is the means by which you create spin states that are far from thermal equilibrium. And if you inject spins into material, there are a lot of means by which you can study non-equilibrium physics. That's really at the heart of many applications in quantum science. And besides everything else, there are also a lot of applications in MRI. And so in this talk, I will sort of more or less focus on a few of them and give you a flavor of where we are going with this. And I want to emphasize that, hyperpolarization is a very wide field, and there are many approaches to hyperpolarization, including the kind of things that Thomas does, which is hyperpolarization using single states of hydrogen gas, which is a really amazing technique. And here optics is used for polarization. It has some advantages in the sense that if you keep the light on, the polarization is maintained forever, so it's sort of replenishable. And the polarization is generated in a solid state medium, and the solid state medium can be physically moved. And so here are some special features of the system. So in any case, maybe in this talk, I'm mostly going to focus on this top part here, which is how to polarize spins and how to see them efficiently in this material. So I just wanted to give you some background, to give you some idea of how one could potentially do this. And actually, all these properties that we saw stem from the special properties of these defects in diamond. These are NV centers, and they became very popular for quantum computing, but it was realized that the same properties that you use for quantum computing can be used for a patently classical task, which is NMR. So these defects are basically where you take a carbon atom, you replace with a nitrogen atom, and you have a vacancy nearby. And they have two very special properties. One, you can polarize, so these turn out to be electrons, and they spin 1 electrons. And that's like a generic structure of a spin 1 electron with zero magnetic field. It turns out if you shine light on these spins, you can polarize the spins with light. So you can put 100% of the spin population of this electron in a particular spin state. And the amount of light you require is very little, and so forth. And this can work at room temperature and zero magnetic field, so it's very, very forgiving. If it was only this is interesting, but it's not as interesting as if you can combine it with the second property that these defects give you for free, which is you can read out the spin state with light. And it turns out that these spins fluoresce very brightly in the red. And the two spin states here, so this is spin 1, so this is labeled ms equal to 0 and ms equal to plus minus 1. So these two spin states have a slightly different fluorescent contrast. So there is a spin-dependent fluorescent contrast. One state is bright and one state is dark. I mean, it's not completely dark, it's slightly darker. And you can tell if a spin is up or down based on the fluorescence that you collect from the spin. These two features together have what have propelled these NV centers as a sort of prototypical system for making these quantum sensors. I don't want to go into too much detail, but I want to give you a flavor of why this works. And I want to also emphasize this is not special to diamond alone. So several other systems share this sort of general energy level structure that makes it happen. But generally, the NV has a ground state, which is a triplet. It's a spin 1, and it's got an excited state. So it's got a collection of levels here at room temperature. And when you shine green light, you're actually shining light that's beyond the band gap here, beyond the gap here, energy gap. And you shine, and if you start with the ms equal to 0 state, you do a cycling transition. So you go up and you come down. However, if you start with this ms equal to -1 state, you go up and come down, but with some probability, you go into a singlet state. And this singlet has two important properties. One, that it's non-fluorescent or non-radiative. So when you look at the fluorescent counts from, starting from 0 or -1, you get lower fluorescent counts if you start with -1, just because for some probability you go through a state that's non-radiative, and so it does not produce any fluorescence. But a second very important property is the singlet state selectively relaxes only to the ms equal to 0 and does not come back here. If you start with the ms equal to -1 state, you go through this path, but you finally land up back in this ms equal to 0 state. And so this setup sort of sets up a bias in the system. So if you keep the light on long enough, and you don't need to keep it too long, but if you keep it long enough for about a microsecond, then all the population is selectively shunted to this ms equal to 0 state. So you can produce electrons which are highly polarized, almost 100% polarized, all in this one state. And along the way, you can also read out the electron spin state, because if it started from here, it would produce lower fluorescent counts, and you can read out that the electron started from here. This very simple kind of toy model is what makes all of this work. Finally, all the NV spins are polarized to this level. And during this process, you can get a readout contrast between the 0 and -1 states, which is what you use. So we are actually going to exploit a large part of this talk, the property that this NV center spin can be optically polarized. People in the community became very interested because here's a spin. It's easy to prepare. You can bring it close to a surface. It works at room temperature and Earth's magnetic field, so it's almost benign. And we buy these materials from drill bit companies, so it's very easy. You just buy it. And it's compelling to consider whether you can take these NV centers, shine light on them, so they align, they spin polarize 100%. But if you've got nuclear spins in their surrounding, then they are not polarized at all. So even at something like 7 Tesla, the polarization, which is the alignment of these spins, is only a few parts per million. So the question is, and here's the question: can you actually transfer spin alignment or polarization from the NV centers to nuclear spins? And do this at room temperature and Earth's magnetic field and so forth, and do it in very benign conditions, and be able to enhance NMR signatures of these nuclear spins. So this was got the community excited, and a lot of people were trying to polarize from the NV center directly to analyte nuclear spins. But it turns out that these NV centers, although they have very nice properties, they come with a very small concentration in the lattice. So they're only in about a part per million or so physically in the lattice. So you take a diamond, and they are that's why they're defects. So it's not like the diamond is made of NVs. These are defect centers within the lattice, so they're low in concentration. So what we started to do was to try to envision whether we can use a nuclear spins as a relay medium to transfer polarization from the electron, which is the NV, to an analyte of interest. And there are some advantages of using the nuclear spins, which is they are very abundant. They can be present on the surface. You can even make a diamond. So this is a cartoon, but you can take a diamond particle and grow on it C13 diamond. So you can make a diamond on diamond growth. And this thing could be enriched with C13. So you can have 100% C13 on the surface. So you can have very high amount of concentration of C13. And they also are very coherent and have very long relaxation time. So you can get all the nice properties of nuclei. Apart from the fact that you can have very high surface area, and these particles themselves can be functionalizable, so you can move them wherever you want physically. So what we started to do was to try to envision this sort of cartoon, which is you have a bed of nanoparticles of diamond, you shine light on them, the NV centers polarize, and you sort of transfer polarization to the carbon, and from the carbon to the outside world. You know, so this is I should lay out that this is sort of a difficult problem because of very special features of these materials, and I'll go in more detail. But what we've been able to do so far is really show that the carbons in the diamond can be very, very highly polarized, including on the surface. And now what we're trying to do is actually polarize materials with it. And so the key challenge in this entire enterprise is the fact that while these NV centers polarize, I didn't tell you in which direction they polarize. So if you shine light on these particles, or shine light on diamond, the NV centers are quantized in a very specific direction in the lattice. And this is one of the problems of a solid state medium. So solid state media give a lot of advantages in transportability, and it's really a physical thing, so you can move it, unlike a gas or a liquid, you know, which is more difficult to kind of physically localize. Here, a solid state medium is a very physically amenable to all kinds of tricks that you can do on the outside. But the problem is that there is a definition of a lattice, and the electron is quantized in a specific lattice direction. So it turns out that if you have a collection, so when you shine light on these particles, they polarize in a direction given by this N to V axis. And this is not so much of a problem unless you consider a large collection of these NV centers. So if you have a large collection of these NV centers, or a large collection of nanoparticles, then every nanoparticle has a slightly different orientation, and you cover the entire gamut of orientations. And so all these NV centers, while they're all polarized 100%, they're polarized in a local axis that has no correlation with an external axis. So another way to say it is when you look in frequency space, the electronic spectrum of these NV centers is very broad. So it's orientationally broadened. And this is true for sort of any spin 1 electron or spin 1 spin in general. You've got a very large anisotropy. So the spins are very broad, and it's very difficult to control them. So even in a modest field, you know, you've got like a many large gigahertz coupling spread in electronic spectrum, ESR spectrum. So it's very difficult to control these spins. So instead, what we want to do is to take all the carbons which are in the diamond and align them all in one direction. So you've got these NV centers which are polarized all in random directions. If you have a microscope or if you have a magnifying glass and you can go down into the lattice, you can see all the NV centers spin polarized, but they're polarized in random directions. And what we want to do is convert this order that exists at a sort of nanoscopic length scale and convert it to magnetization of nuclei which are all in one direction. And it turns out that that is actually possible if you just operate at a slightly different magnetic field. And I'll show you why, but the insight is to operate at a slightly weak magnetic field, in which case the broadening is not so much. But we came up with a very simple protocol that achieves this. And I just want to walk you through the protocol and show you the results here on the right. But what it involves is a continuous irradiation of laser light, fairly low in power, and a chirped microwave excitation. So this is a microwave frequency on the x-axis, time on the x-axis and frequency on the y-axis. So you're chirping frequency of microwaves at low magnetic field. And we then carry the sample to high magnetic field, so to get a control experiment. So you can see how much of the spins are actually polarized when you transfer them to a magnet. Here are some typical results of some particles here. So this blue line is an NMR signal from about 1 milligram of diamond, and that's a very weak signal. That's 7 Tesla. So I think that a few hours of averaging gives you that kind of SNR. And a few seconds of optical pumping can give you that kind of signal to noise. So the spins are very highly polarized. And you can show this polarization by many ways. You can say how much it's polarized over a particular field, over the field at which it's polarized. It's pretty large, or effective time savings and so forth. But overall, though, this should not come as a surprise, and that's because the NV centers are very highly polarized. And what you're trying to do is transfer the spin order in the NV centers to the nuclear spins. The bigger surprise is that the NV centers in this random collection of particles are polarized randomly, and why all the carbons are polarized in the same direction. I think that's the big surprise, and I'll show you why that works. But very importantly, this protocol itself requires very low power, so it's very easy to manufacture. So it's only for a 1 micron particle. So for one 1 micron particle, a typical sort of nanoparticle, let's say, it's 30 nanowatts of optical power and 2 nanowatts of microwave power. So it's very easy to accomplish in the real world. And I want to show you why that works, but let me just show you some other interesting features of this mechanism. So I told you that you produce spin polarization by swept microwaves. And it turns out if you sweep the microwaves one way, the spins polarize in one direction. But if you sweep the microwaves the other way, the spins polarize in the opposite direction. If you sweep the microwaves in a sawtooth pattern, the spins don't polarize at all. So actually, you can control the sign of the sign of the spin polarization. We have a weak magnet here. This magnet is a refrigerator magnet, about 10 millitesla or so. But the spins polarize aligned or anti-aligned to this magnet, or anywhere in between, just by the direction of these microwave sweeps that you apply. And these microwave sweeps are very low power, very low frequency. You just are almost tickling the spins, but you can sort of make them very highly polarized through them. In this slide, I want to give you some flavor of the physics that happens inside the system that makes it work. And the important challenge is that the NV centers are randomly polarized, but the carbons all land up to be polarized in the same direction. And this is the main physical sort of interesting part of the system. And this actually works because we work at low magnetic field, and there's a hierarchy in the energy levels. And this is what makes it work. This is a very special sort of regime that's opened by these NV centers, and by the fact that you can polarize them at very low magnetic field. So here is an energy level structure of a single NV coupled to a single carbon. This is an electron, this is a nuclear spin. And electronic spins are much larger in energy gap. So you've got the manifold of nuclear spins with the electron at 0. And this is a manifold of the nuclear spins with the electron at -1. But very importantly, this energy gap is smaller than that energy gap. So when you work at low magnetic field, you can turn out this energy gap is only set by the Larmor frequency, or the Zeeman interaction of the nuclear spins. But this energy gap is set by hyperfine couplings that can be larger. And because of this difference in energy gap, okay, so this is the MS equal to 0 and MS equal to -1 branch. You can set up a bias in the system. How I like to think about hyperpolarization is that you have to introduce bias in the system. So you start with spins which are unpolarized, which means that these two spin states are equally polarized. So also these two spin states are equally polarized. So when you shine laser on the system, all the NV spins are polarized to this manifold. So you don't have any population here. You only have population here. But between these two levels, which are very close in energy, they have almost equal, to within a part per trillion or so. They have almost equal population. So there's no population difference between them. So but you can hyperpolarize the system if you can introduce bias. So you want one of the spin states to go in a different path compared to the other. And if you can do this, then you can somehow set up bias so that all the spins, all this population sort of travels to one of the spin states and not the other. And that's what happens. So it turns out if you write down the same energy structure in the rotating frame, and this is a picture in the rotating frame, as you sweep the microwaves, you get these level anti-crossings. And the fact that you get level anti-crossings is not surprising, but what's interesting is that you get level anti-crossings for which the energy gap is a function of the spin state. So if you start with the spin state up here, you've got a large energy gap. And if you start with the spin state down, you get a small energy gap. And all of us know that if you traverse an energy level anti-crossing, the traversal can be adiabatic or diabatic based on the size of the energy gap. And if you're adiabatic, you more or less remain within this branch. But if you're diabatic, you sort of split the population between the two branches. So what happens is that in these two spin states, the traversal through one of the spin states is adiabatic, and the traversal through the other spin state is diabatic. And as you traverse the system, most of the population that's in the spin up state remains in spin up because that's adiabatic. But this population that spin down splits between down and up. And over time, you build up a ratchet, and all the population is transported to this down state. And this is what gives rise to hyperpolarization. So, at its heart, it's a very simple mechanism, but it's the same thing that works in all hyperpolarization mechanisms. It's a means by which you can build up a bias in the system. So in any case, it turns out that because of this fact that you do it at room temperature, low field, etc., it's very easy to generate polarization. And light also is very special. There are many ways by which you can deliver light to a system. So in any case, we built this small polarizer device. So this is about the size of a shoebox, and it's supposed to, you can put nanodiamonds into it, and you press a button, and you can polarize these nanodiamonds very highly. But the important thing is the very benign conditions in which it operates. Very low magnetic field. It's a magnetic field of a refrigerator magnet. Very low laser power. So it's a small laser diode or LED, basically. Very low microwave power. So just a Wi-Fi microwave amplifier, works at room temperature. It's a very small device. This is what the device has, but it has a laser and microwave sources, which are small chips, so like in what's in your iPhone, basically. So that's this was our old design, and now we have moved on to a more interesting design for polarizing large masses. And this is one of the special features of optics, and especially because the optics here can be very forgiving. All you need to do is illuminate the spins. You can illuminate them with any sort of light you want. It helps if you illuminate them close to green, and you can also illuminate them. Coherence of the light source is not so important, so you can use a lamp, you can use an LED, you can use a fiber laser. So we're using actually 30 lasers all in a dome, and so it looks like one of these fusion experiments. And the goal here is to polarize a very large diamond mass. So we are able to polarize more than 100 milligrams of diamond all at once by applying 30 lasers all at once on the sample, and then actively cooling it and whatnot. But it really shows that this mechanism of polarization per diamond spin is very low power, but also the sort of the flexibility of optics allows you to do all kinds of crazy things, and you can deliver polarization either selectively to a particular particle or to large masses, and it's very easy to design these systems. So these are fiber lasers with a single diamond in the center, diamond nanoparticles in the center. So let me show you some applications of what you can do with this. So the simplest application is in MRI, and it's quite obvious because MRI is an imaging version of NMR, and because these spins are very bright in optics, bright in NMR, you can also make them bright in MRI. So here's a very simple proof of concept experiment. We have a ring, and we filled this ring with diamond particles. This is one of the good things about diamond particles. They fill whatever volume you want them to fill. And so you can make them fill this volume. You can see them very bright in optics, in fluorescence. And this is obvious because these particles fluoresce very brightly. This is a simple fluorescence picture, but you can also see them very bright in MRI. So you can get a picture of these particles in two different modes, fluorescence and MRI together. And normally the MRI image is not possible to get, but with hyperpolarization, this is not so difficult to get. And then you might say, this is cool, but what is it useful for? And actually, it's quite interesting for two reasons. First, this is a dual mode imaging. So you can image the same object, which is a diamond particle, in both fluorescence and MRI. This is cool. But now there's a chance by which you can combine these two modes. And these modes actually have a very important and special feature. And that is fluorescence imaging happens in real space, which is, you're just looking at the object and you're imaging in real space. MRI actually occurs by imaging in K-space. So the way MRI works, you're applying gradients and you're looking at a slice by slice of the image in a Fourier reciprocal space of real space, or K-space. And then you do an inverse Fourier transform to obtain the image in real space. Yeah. So optics and MRI are two imaging modes, but they occur inherently in two Fourier reciprocal spaces. And now you can imagine that the same object is bright in two Fourier reciprocal spaces at once. And this is very special because you can exploit this to get speed up in imaging, because if you've got a very sparse set of objects that you're trying to image, if it's sparse in real space, then it's not sparse in k-space. And you can use this property to accelerate imaging. You can also use the simple fact that optics imaging has very high spatial resolution. So you can really get down to a diffraction limit, which is less than a micron. But optics suffers from optical scattering. So if you try to image particles in tissue or in milk, or any sort of a real world medium, the resolution blows up exponentially. So you're going to get very poor resolution when you image an object through a real world medium. But MRI is RF imaging, and MRI does not suffer from scattering. So there's a chance by which you can combine the good features of optics, which is high signal to noise, with MRI, which is the fact that it's scattering free, and combine them together, apart from the fact that you can get this Fourier conjugacy. And we're working on many special features of this system. But this shows a very simple means by which you can maybe make contrast agents that are bright polarization contrast agents. And these particles can be delivered into materials and tissue and cells. I also want to show some very interesting new results out of these particles, or out of the system. All the results that I showed so far is a classic pi-half acquire of free induction decay. So all the signals that I showed, they are hyperpolarized, they are very large signal. But what you're doing is a single pi-half pulse, the spins process in the magnetic field, and you're collecting the fluorescence, you're collecting the free induction decay. And these spins decay very fast, usually in less than a millisecond, because they're all coupled to each other. And this is what you do a Fourier transform of to get the spectrum. And this is the NMR spectrum. So we started investigating whether there's a chance by which we can improve the readout. And as you can imagine, this is very useful even in MRI. So all of these pictures that you got here were all taken with a single pi-half acquire effectively. This is a typical signal that you get. It turns out that you can actually use the long coherence of these nuclear spins inside the solid, and the fact that they're coherent for free without you doing much in a protocol that's a variant of what's called spin locking. And then you can hold the spins from decaying for much longer. So this is a time trace of a normal hyperpolarized spin decay in a solid, which decays very fast, but you can actually hold them for much longer. And it turns out that you can hold them for very long. So this blue line here was all the results I've been showing you so far. And this is a time. And so this decays very fast in under a millisecond, but you can hold this for a few seconds easily, approaching 10 seconds now in our new results. So it turns out now if you do a full, and this is a one-shot signal, so there's no averaging here. This is this kind of signal that you get in 10 seconds of optical pumping, so very high signal. If you do a Fourier transform of this, the blue line gives you the old spectrum, which was hyperpolarized, which was very nice, and which we were very proud of for a long time. But now that's blown up about 10 times. But this is the new signal that you're able to get as a result of this this protocol. It has two advantages. One, you get very large enhancement in signal because you can collect the signal for this 10-second period instead of 1 millisecond period. But you also get a very large line narrowing because the spins are inherently very coherent and you can hold them for a very long time. And I should mention that this is not very special to diamond. It's actually quite a general property in solids, and this was investigated back in the 70s and 80s. But what's special here is that we can marry it together with hyperpolarization in a nanoparticle or microparticle platform. So it allows you to obtain a very high fidelity NMR signal of these nuclear spins, which are usually quite inaccessible, but because you can polarize them with light and you can see them with these enhanced readout techniques, they become amenable to using them for some physical tasks. So the protocol itself is a variant of some older ideas, but applied now to this newer system where you can get very high single shot. So this is a single shot SNR, about 1 milligram of diamond. So you can ask what you can use this for. And we are very interested to use this for sensing, or actually you can use spins as sensors themselves. And let me just give you a flavor of how this works. So any spin is a kind of a two-level system, and you can make it a sensor. And this is very simple. So it need not be, it's agnostic to whether it's an electron or a nuclear spin or any, more or less any spin, or any spin that you can write down as a two-level system can be made into a sensor. And it's very simple. So if you're trying to measure DC magnetic fields, Then if you prepare the spins in a superposition state and you let them precess, then if you apply a magnetic field during this precession period, then this precession frequency changes as a function of this applied field. And so the magnetic field is encoded in the precession frequency, which then can be converted to phase, and then from phase to population. And this was a technique due to Ramsey in the 50s, very, very simple. It allows you to measure a kind of static magnetic field applied to any spins. As long as you can read out, you can prepare the spins efficiently in a spin state, and you can read them out efficiently. This is a very simple idea. You can also measure time-varying magnetic fields. And you can measure time-varying magnetic fields by doing the same trick here, but applying a pi pulse. So you only allow the spins to be subject to interactions that have a period that's given by this period tau here. And once again, the magnetic field information or the amplitude is imprinted in the phase of the spin, which then becomes a spin population, which you can read out. So while these ideas have been around for a long time, it was realized that because of the access to these new systems, both electrons as well as nuclear, you can now make new sorts of spin sensors with these systems. And while it's written as magnetometry, which looks a very physicsy thing, NMR detection is in the end magnetometry, because you're measuring in NMR the weak magnetic fluctuations of nuclei, which produce a very weak magnetic field at a particular sensor site. So if you can make a very sensitive sensor, you can also make an NMR sensor or an EPR sensor, so you can use it for kind of chemical sensing tasks. So here is an example, and this has become quite popular now in the NV center community, but you can use a single NV center close to the surface of diamond, and you can measure nuclear spins in its surroundings. Because of the fact that these nuclear spins produce a very small but fluctuating magnetic field at a very fixed frequency given by the nuclear Larmor frequency, and because you can read out and prepare these NV center electrons, you can obtain an NMR spectrum of its surrounding environment. And there have been many groups working on this, but these results out of Harvard have been very nice, and they show NMR detection out of picoliter or so volume that has all been taken with optics, so optical NMR detection using NV centers. And this is quite a burgeoning field. And this allows you to take, the main advantage is it allows you to make NMR sensors at a length scale that's inaccessible from current NMR. And that's because the NMR detection is done with light. So you can really localize the NMR detection to either a surface or an interface, or generally to a volume, which is between tens of nanometers to, in this case, about 20, 30 microns in size. But while here the NV center is used as a sensor, there's no reason why you can't use the nuclear spins themselves as sensors too. It's because this property of spin sensing is agnostic to whether you use an electron or a nuclear spin. It just requires you the ability to prepare a spin in a particular state, as well as to read it out efficiently. And because we can read out these nuclear spins and with very high fidelity now, with very high SNR, we can use it as a spin sensor, and that's what we're working on in the lab. It turns out if you write down the same sort of spin locking pulse sequence that we described before, this protects the spins against all interactions except magnetic fields which fluctuate at a very specific period. And it turns out that the same experiment, so this is not data, this is simulation, but it's basically the same idea. You can show that if the spins are subject to fluctuating magnetic fields of any origin, either artificially produced or through nuclear origin, or through electronic origin of this particular frequency, then the signal here will be reduced quite a lot. And the change in either coherence time or the signal can act as a proxy for you to detect these spins. And this is what we're working on. It turns out that this has some big advantage over the NV centers in the sense that this carbon-13 is spin half, so is independent of orientation. And this allows us to make NMR and EPR sensors in nanodiamonds, and these nanodiamonds can be transported physically to a material of interest. And for experts in the audience, it turns out the NV center cannot be used in nanoparticle form as a very good sensor because of this orientation dependence. Let me just conclude by showing you some ideas of what you can do with these transportable sensors. So we've been playing around a lot with the very nice properties of nanodiamonds. So this is a movie again of these red things are nanoparticles, and you can see droplets. This is a droplet of water and oil, but this shows a blow up picture. And this is grayscale, but if you see it in fluorescence, it's even clearer. But these are droplets about 10-15 microns in size of water and oil, but inside them have been seeded a specific number of nanoparticles of diamond. So there are like here, these are I think 1 micron particles, but there are diamond particles in them here. And you can really make very reproducibly equal some number of particles, and these particles are sampling the volume of these micro droplets. You can also, so in this regime here, you have a single droplet that has a countable number of these nanoparticles. You can also go to the opposite regime where, as here, we've taken a microfluidic droplet of water and oil, and by controlling the surface hydrophilicity or phobicity, we have been able to dress the droplet with nanoparticles of diamond. Yeah. So this is a water droplet with nanoparticles dressing its surface on the outside. And you might ask why these are, what's interesting about them. So what we envision using this for is as a transportable magnetic field sensor. So you can basically seed the particles in this vehicle, and you can move this vehicle now very easily through all kinds of tricks, electrostatics and whatnot. You can write your name with microfluidic droplets by making them move in any path of interest. And this allows us to make distributed sensors. So you've got a nanoparticle in each little droplet that can act as a sensor that can be read out through optics. But you've got an array of these sensors, and the array can be made in any configuration that we want. So you can make an equivalent of a spin radar, equivalent to how radars work in the real world, but you've got a phased array of these sensors, and you can read out the signal from each of these sensors and then manipulate the phase at which you read them out, so you can control effectively the sensing pattern of these spins. And in this regime here, we've got nanoparticles of diamond that are dressing the droplet, and we want to use it as a means by which we can polarize materials inside the droplet, as well as study the surface of the droplet itself. So in this configuration, when you shine light on the particles see all the light, and the material inside could be opaque, there's no problem. And the polarization can then be funneled from the outside, from these droplets to the inside. It also allows you to study many interesting things about droplets themselves, including reaction acceleration in droplets. There's a lot of interest now in reactions that have been shown to be accelerated, and there's a lot of hypothesis about these reaction accelerations originating from electric fields on the surface of these particles, and we want to use them as electric field sensors so that you can measure electric field on the surface of these droplets. But generally, what this illustrates is because you can exploit through light the excellent spin properties of these materials, and these are materials in the solid state, these materials can be physically transported, and you can actually put them into things. And this is a very simple example of that. Let me just conclude by bringing back this slide. So I want to emphasize that this is a very active area of research, and we are not the only people doing this. This is a very active, nice, and very welcoming community of people. I think this is an exciting system, partly given by the forgiving properties of the material system itself. So a nanoparticle with very nice nuclear spin properties and electronic spin properties, and the ability of the nanoparticles to be functionalized. And so together, in general, we envision means by which we can produce deployable NMR sensors that can be brought into materials. And opening applications potentially in hyperpolarized materials, in sensing, also sort of NMR detection of very short length scale materials, transportable sensors, and things that we didn't talk about today, which is producing spin injection in materials of interest. Yeah. So let me acknowledge, so we have a large group, but a lot of the research that you saw today was actually done by all undergraduate students at Berkeley. Berkeley is a large school with very smart kids and very fearless. So here are all the people who contributed, and here are some of the papers. So thanks.
Yeah, thank you so much, Ashok. Applause. Sorry, it's kind of hard to do applause here in real time. Absolutely amazing. Thank you so much for such a.
So yeah, feel free to ask any question. And
yeah, absolutely. So I do very much encourage maybe everybody who's not too shy to maybe turn on their videos and maybe unmute yourselves so that we can have some conversations here with Ashok and maybe some kind of leisurely talk about various ideas that we can discuss here. So may I ask if there's any people that have any particular questions?
Can I go first?
Yeah, anybody can go. Yes, go ahead.
Okay. Okay. Yeah. Thanks. So nice talk, Ashok. My question is: so you talked about optically detecting via gray versus weak versus strong fluorescence, and then you switch to the spin lock. The spin locking experiments, were they done at 7 Tesla with regular RF coil detection, or were they optically detected?
So yeah, that's a good question. So right now it's all RF, and this is, but it's also possible, and we're working on it, to transfer now this information to the NV center and read it out optically. So both modes are possible, but if you use the nuclear spin sensors as sensors, nuclear spins as sensors, the most obvious way to read them out is through RF.
Sure, but you talked about possibility of detecting nuclear spins using the highly polarized electronic spins via optical sensing.
Yes. Yeah. So let me just go back to this one second. So there are two modes, right? So it's a little confusing. So one, you can use the NV center as a sensor, and this is all done through optics. So the nuclear spins process, the nuclear spins which is in the target, in the analyte, and they process and they produce a fluctuating field on the NV center, and this can be read out optically. Yeah. And this spectra here, I like to say this is a kind of the most simplest NMR spectra ever published, published in Nature. But that's because they were able to see these NMR spectra in light. So that's very interesting and exciting, and in a very small volume.
I see. So that would preclude like imaging in bulk media.
Yeah, so here I think the particular niche of this sort of NV center mediated optical NMR is really NMR of very small volumes. Inaccessible. So one of the frontier areas that our community is working on is NMR of one cell. So you put one cell on top of the diamond, and then you're able to image through NMR different parts of the cell, and in every pixel of the cell you get an NMR spectrum. Stuff like this, which is outside axis of current NMR. I think that's a particular niche of this regime.
One more question. So you showed an RF coil in your second slide, I believe. Is this the coil used in your RF detection?
Yeah, exactly. Yeah. So let me go back quickly. Yeah, but it's a very crappy coil. It's a coil I made myself, so it's not very great. But
so is this a printed coil? Is this a printed?
Yes. So here, this is a coil actually we printed with copper adhesive tape. With a little artist's printer, it's not very great, but you can see that the system is so forgiving that you can get all these high signals even with this coil.
This is a great coil. I mean, we will make the same coil as well.
Okay,
so, we'll probably ask you about the details how you printed it.
Yeah, there's a little video on YouTube on how we printed it. One of our undergrads made this, but it's actually just with this. You can make these little printers with a knife, and you can just cut. It's very easy to make.
All right. Thank you.
So Ashok, I had like a sort of a kind of maybe a slightly silly question. So one thing that was curious to me is like the transition going from the small sample sizes to larger sample sizes for hyperpolarization, and then maybe also the increased amount of power of light needed with the various lasers. So while you were talking, I was just kind of doing like a small little calculation of like a typical, liquid state sample where you would maybe have like 100 millimolar solution, and let's say you have 1 milliliter, then there's like 10 to the 21 particles, roughly speaking, in there. And so if I calculate the number of photons needed to polarize all those spins, then that's on the order of like 100 watt, if you assume that, you're dealing with relaxation times on the order of a second. So to hyperpolarize all of them to achieve 100% polarization. So if you assume you have, perfect quantum yield, like that every photon actually produces a hyperpolarized spin. So my question is, just how much power are you trying to dump into these samples in your new iteration of your device that you showed us?
Yeah, so this is a new iteration, and it's a very good question. So larger, so although per particle, the thing is quite efficient. So first of all, we need to the T1 of the effective T1 of these spins is tens of seconds, 20, 30 seconds. So
That's nice. That gives you already some space. Yeah,
that gives you some space. But here we're actually dumping 30 watts or so into the sample.
Okay. Good.
Yeah.
Okay. So you
but it turns out that we have a very elegant design. So this is a 3D printed refrigerator, and you use the fact that actually diamond is a very good heat conductor and can conduct away heat, and you can suck it out and whatnot. So yeah, it's 30 watts, and these are all fiber lasers. And yeah, our limit of our system is 60 watts at the moment.
Yeah. Wonderful. Okay, that makes good sense. Thank you so much for the explanation. Maybe the grad students, are there any questions from the grad students that maybe are interested in similar experiments and asking questions?
Hey, this is, oh, sorry, go ahead.
Maybe it's a general question. What dictates the relaxation time of the spin? You mentioned that it is millisecond, something like that.
Yeah, so it depends on which spin we talk about, but I actually have a slide on this. Let me just show you quickly. The relaxation time of the nuclear spins can be very long. It's field dependent. Okay, this is what the slide is showing, but it's very, very long. It can be tens of minutes. The relaxation time of the NV electron is about a millisecond. This is roughly the time scale. But if you talk about the nuclear spins, this was a kind of surprise to us. So this is if you just talk about a two-level system of nuclear spin, you can ask what is meant by relaxation. Is basically any process that can cause the spin to flip, right? So we then, because you can hyperpolarize the spins, you can actually study T1 as a function of magnetic field. And we did this very carefully. And this is a typical graph that you get. Okay, so this is different samples are different, but this is a graph in an enriched sample. So it's a large number of C13s, but this is T1 as a function of magnetic field. And you can see that it's got a very special shape. It's got a shape of a knee, almost like a step function. So it turns out that we understand why this works. And that's because the lattice contains other paramagnetics, which are not NV and which are called P1 centers. So Alex Spinov knows all about them, but they are EPR active paramagnetics, which cannot be optically polarized. And it turns out that you can have a 3-spin flip process. So 2 P1 centers want to flip, and they're slightly energy mismatched. And to flip themselves, they flip a carbon. So if you're a carbon, you're a peaceful guy, but you see sort of spin flipping randomly coming from the P1 centers. And this is what causes this mechanism. So this is good news because it turns out if you take pure diamond, this mechanism does not exist. And then you can have a pretty large coherence T1 times in these materials.
Thank you.
Well, hi, Ashok. I have a question. You had mentioned other materials such as, and I know one of them is silicon carbide. I'm just curious if you've done any experiments at all with alternative materials, and if you have a feel for like what is the advantage of maybe an NV or a disadvantage of an NV compared to alternatives that do the same thing?
Oh, this is a very good question. So it turns out that the properties we're exploiting here are twofold. One, that the electron can be spin polarized, and second, the electron can be read out with light. Right? So especially if you want to use it as a sensor. But if you simply want to use it as a polarizer, you just have to use the fact that the electron can be somehow polarized with light. And this is a very much more relaxed set of conditions. And there are many systems that can do this at room temperature. Silicon carbide is one of them. The advantage of silicon carbide is the wavelength required is in the infrared. So it can penetrate much better. Also, you're not tied to the diamond industry anymore, and silicon carbide, you can get large wafers, 4-inch wafers of silicon carbide at very low cost, so etc. So there are a lot of advantages of the material, and these electrons can be spin polarized, so-called V1 defect in silicon carbide. The disadvantage is very difficult to enrich silicon carbide because silicon carbide is tied to big industry making heat, MOSFETs, high power MOSFETs, and basically it's very difficult to get people to do any lattice change. And so it's very difficult to get lattice. You can buy stuff that already exists, but it's very difficult to change things. But in general, though, optically polarizable electrons are wider. I know even these triplet systems like in pentacene and anthracene and whatnot, I think there's a large collection of electronic systems that can be optically polarized, and we are exploring some of this now in our new lab.
Thank you.
I have a question about it. Nitrogen. You have nitrogen right next to the electron spin. Can the spin of a nitrogen used in a useful way to manipulate the spin system?
It's an excellent question. Excellent. So, this nitrogen can be N14 or N15, and usually it's N14, and which is, it's a spin 1. It has three transitions basically, and we see this all the time. People doing NV detection see these N14s a lot. The problem with them is, so they're not too useful. They're useful in the sense that you can make a very good memory with them. So people have used them in the past when you have information that's stored from the NV center. You can store them in the N14 because they'll live longer and whatnot. But the main reason why they are not as useful as C13 in this case is because they are not so abundant. So every NV has an N14, but that's all. But the number of NVs is only a part per million in the lattice, between 1 part per million and 10 part per million. But C13 is what makes up the lattice in the first place. And you can make diamond out of pure C13. So there are way more larger number of these nuclei. So it's easier to see with NMR, and it's easier to manipulate. So that's basically the difference between them.
Thank you.
Can I ask one more question?
Of course.
So you polarizing the neighboring C13. I mean, does it go in the classic DNP mechanism? So first you polarize nearby C13 and then it goes by spin diffusion?
That's
or
right.
Is it simultaneous magnetization? How does it go?
So it's a very interesting question, and actually in the whole DNP community itself, this is a big raging controversy. How important is spin diffusion? So generally, spin diffusion is a very important thing because the number of electrons is few, and in this case, it is indeed the case. You've got like 1 or 10 part per million. So you take a million atoms in the lattice, only one of them is the polarizable electron, and everything else are nuclei that have to be polarized, and they have to propagate through internuclear couplings. The question is, how important is it? And we've done some recent work. It turns out that these P1 centers, which are sort of, usually considered to be useless and just lying around, can play a role to accelerate spin diffusion because you can have, the P1 is an electron, and this electron has a wider reach in the lattice. So electron can see 2 nuclear spins, even up to 10 nanometers. And one nuclear spin can transfer its polarization transiently to this electron, which can then pass it on to another nucleus. And so it turns out that potentially these electron-mediated spin diffusion can be faster than pure nuclear spin diffusion. But this is a difficult question to answer because it's very difficult to see intrinsically what's happening in the lattice. But there are some indications that this process is operational here.
Right, but you could measure time-dependent build-up, and if it's seconds or longer, then it's probably spin diffusion, not like the transient flips that you mentioned. I mean, what's your time constant for the?
So the time constant is usually just set by the T1 of the nuclei, and this is about 10 seconds or so, 10, 20 seconds. But why we see this transient is because you can actually pulse the P1 centers. Yeah, you can manipulate them during the process of. Yeah, so you shine light on the NV and you have all this polarization going, but you can also do stuff to the P1s, and you see then the polarization is reduced. So you can actually you can coherently manipulate. You can do tricks and you can try to see which path it's going through. But in general, given a large system with a large number of processes, I think they all are operational. It's just that they are at different weights. It's like water sloshing in a tank. I think there are many paths it can go. But this is very interesting, and this is one of the things we're trying to study basically by producing a non-equilibrium spin state. So we're producing spin texture of like an onion shell of polarization, and we're trying to see how this spin texture diffuses in the lattice.
But if you can stop it, then that means it's probably not spin diffusion, because if it were spin diffusion, it would just continue growing. If you can almost instantaneously stop it by operating the optically the NV centers, then it's probably the long distance, 10 nanometers, maybe longer coherent flips.
Yeah, I didn't mean you can stop it. So by operating the P1 centers, you can reduce the effective polarization or the rate of polarization. You can stop. But indeed, the NV is seeding the polarization. So if you switch off the NV, you don't shine light on it anymore, then then you get a rate constant, which is just spin diffusion related, and this goes in a few seconds. Yeah, so I think both processes occur, and what we're dealing with here, unlike conventional DNP, is a slightly lower T1. This is the main problem of these optical systems. We are forcing ourselves to work at room temperature, to get all the properties of room temperature, transportability, targetability, and whatnot. And because of this, we hit ourselves in T1 compared to other people who work at 1 Kelvin and get infinite T1. And this is slightly a problem in this system.
Okay, thank you.
Excuse me, may I ask one question?
Of course.
Go ahead, Julia.
Okay. Ashok, thank you so much. This is a great presentation. And I saw that you mentioned some kind of intermediate step, right? So you're going to you transfer polarization from diamonds to carbon-13, and then the final step from carbon-13 to analyte, right? Could you please go over again how to transfer polarization from the second step to the last step?
Oh yeah, so this I should caution. I don't want to give the wrong impression. So we haven't done it yet, but we haven't tried much too. All this is fairly new. But what we want to do is we actually are very because of this T1 reason that we were just discussing, we are actually liaising with growth experts and growing diamond on diamond. So that's our strategy. So what we do is we polarize NB, the carbon in the diamond, and then we grow ultra pure diamond. So this is diamond with no defects. Basically because inside the diamond you've made these NV centers and they're full of defects, and this is what causes the T1 to go down. But we actually grow through CVD growth, overgrow pure C13 with no defects, I mean, to the extent possible. And it's really a question of how you can get epitaxial growth, and with a single crystal this is very much possible to get pure lattice match. And then the idea is that we would transfer from carbon inside to carbon outside, but the carbon outside, which is in the shell, has very long T1 and very high density, so because it's enriched. And then we will try to use CP, cross polarization techniques to go to the outside. That's generally the plan.
That's a great idea. Yeah.
Mm-hmm. Thank you.
So people in South Africa actually in the 90s, between the 80s, measured T1 of pure diamond, and it takes a long time to measure, as you can imagine, because a sample has such a long T1 that you have to dope it with electrons to see an NMR signature. So we want to exploit the fact that some of these pure materials can have a very long T1.
Okay, good. It looks like there's no more questions. So I guess thank you so much, Ashok.
Okay. Well, thanks for having me. It was a lot of fun. Yeah.
We're so excited to learn more about your approaches, and yeah, definitely there's some definitely mutual interest. So maybe we should talk a little bit more in the future. So yeah, just very exciting. So yeah, I'm not really sure how to best end this. We can't go out for a drink or something like that, unfortunately. So I guess all we can do is wish you well and have yourself a drink, that you gave a fantastic talk here at NC State, and we will also celebrate.
Well, thanks a lot. It was a lot of fun, and I hope you guys come to Berkeley sometime. We'd love to host you here.
Yeah.
Yes,
we'll issue a ring check, for next time we meet us in person. Great talk, Ashok. You can, yes, yeah.
Thank you, Alex. Yeah, see you.
Okay.
Cheers. Bye-bye.
Thank you so much.
Thank you.